Okay, in Math 2400, Lecture 17, Continuous Random Variables 5, the Poisson Process. So this is the story. People arrive at the bank. The arrival of each person is a happening that occurs at a definite time. Now let nt be the number of arrivals in the time interval 0t. For each fixed t, nt is a random variable that takes the values 0, 1, 2, and so on. And 0 means that nobody arrives in that time interval. Nt is also a non-decreasing function of t, that time, which means an arrival of a person increases nt by 1, and during those intervals that no one arrives, nt remains constant. Now the set nt, t starting at 0 going to infinity, is an example of what we call a stochastic process. So the Poisson process is some kind of stochastic process, and now there are some axioms that this process, if some process satisfies these axioms, then we can say that it is a Poisson process. Now these are the axioms for the Poisson process. Let me erase this and write them now for you. So let me, because I have some nice wording here. Okay, we say that non-overlapping intervals are independent. What does that mean? It means that events that are defined using non-overlapping intervals are independent. So let me write it down. Like IE, suppose, so this is like a nice example. Suppose I1, I2, IN are non-overlapping. Then events defined in terms of these intervals are independent. And specifically, these events are independent, and we have this P of I1 arrival in I1, that's number of arrivals in interval 1, comma, and I2 arrivals in I2, and dot, 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 and n arrivals in n. This is our ands here, and. So this is like event number 1. This is like event number 2. And event number. Since the intervals are non-overlapping or disjoint, then these events should be independent. And look, we have and. So the multiplication rule applies here. So that's P of E1, P of E2, P of En, which is P of I1 arrivals in in I1 times P of I2 arrivals in I2 times P of IN arrivals in IN. Okay. So arrivals at different time intervals, if they don't overlap, are independent. So there might be nothing here, 10 million here, nothing, 10 million, or something, 2, 4, 5, whatever. So these events are independent. So we will get this multiplication. I'm using that multiplicative law. This happens. 2. So that was the first axiom. And number 2, yes. So number 2 is fix the time t. So t can be between 0 and infinity. Small time interval for t. The chance of one call arriving, sorry, one person, person arriving in the interval is approximately well, I should say this because then approximately proportional to the that's wrong. Proportional to the length of that interval. What I have written here is not what I've written. Which means what? Which means that this P of one person arriving in the time interval t, t plus delta t divided by delta t, that's the length of the interval. This is proportional to the length of that interval. So this divided by this means that this should be the coefficient of proportionality. So it also means that if limit as delta t goes to 0, it gets smaller and smaller, this goes to some lambda. So that is the coefficient of proportionality. And that means number of people arriving, average number of people arriving in that bank. Okay, so this is what it means, that this, the chance, so it says the chance which means probability, this chance means probability of a person arriving, P of one person arriving in this time interval is proportional to the length of the interval, so this divided by length of the interval should be a fixed number. And that fixed number is lambda, and lambda as delta t goes to 0, that is in fact like the rate of people arriving at this bank. And we just go by per, say, unit of time. Now it depends on the unit of time. If unit of time is like hour, then it's per hour. If you take unit of time to be 30 minutes, say, then it's per 30 minutes, depending on what you take as unit of time. Okay, so that is the second one. The third one is similar to this. So let me see how similar that is. Yeah, that's similar to this. So the third one is also similar to this, and that is like this. So fix the time t with t blah 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 for a small time interval derivative, the chance of one call. Not, why have I written one call? That's another problem. It looks like this. One person. And this one I emphasize. Arriving in that interval t plus delta t is negligible. Which means what? Which means this goes to 0. But the difference is that is exactly 1%. That was a person, but I should have written a person. But this is exactly 1%. So this is more than 1% in time interval. That's a chance of more than 1. In fact, it should be more than 1. Yeah, this is more than 1. More than 1%. Yeah, it's 0. And if you remember from the other lecture I gave when I was deriving the differential equation for this Poisson distribution, I used these three. In fact, I wrote down the last two of them in a different way, and I used that. Without using these two and also the first one, I was not able to come up with a differential equation. In fact, I used this fact that if there is more than 1% in that time interval, that limit goes to 0. So I said that we can just choose this delta t so small, so that we can assume that at most just 1% will arrive in that small time interval, right? So not more than 1, not more than 1. So I cannot think of a process that when the time interval gets smaller and smaller, then there might still be more than one thing happening. But, well, anyway. So now, these are the axioms, and now, as I said, I derived the Poisson equation, Poisson, say PMF, in fact, using this, and I also came up with a differential equation for that, using all three of these axioms. So, and what was that? It was that if x is Poisson, well, let's say x is, let me just, so, not x, sorry, I'm using nt. So if nt, so nt will be Poisson lambda t. Remember, lambda was rate. So, and since we are dealing with time interval 0t, so the rate will be lambda t. So let me give you an example. If we say that in average we have 5 people arriving per hour, and if I'm doing some analysis on 5 hours, then that will be 25 people in 5 hours. So that should be multiplied by that time period that we're talking about. So I will give you an example, and this is P of n t equals some j, will be e to power minus lambda t times lambda t to power j over j factorial. And remember that I don't know if I use j or whatever. And n of 1, if I'm dealing with just one unit of time, depending on the unit of time I have defined, that is Poisson of length. So there's also another thing, which this thing I did not discuss when I was discussing Poisson process. So let's look at this amazing property of the Poisson process. So let's say we have n of s plus t. So both s and t are numbers, and we subtract n of s. That is number of people arriving in time interval s plus t, and number of people arriving in time interval 0 to s. This is 0 to s plus t, that is 0 to s. And this is a number of arrivals in 0 s plus t minus number of arrivals in 0s. So that is in fact number of arrivals in s and s plus t. But this thing s comma s plus t has length t, and there's number of arrivals it's like number of arrivals between 0 and t. So it is like number of arrivals in 0t. So this has the same distribution, n of s plus t minus n of s has the same distribution as nt, which is Poisson lambda t. Okay, so that is the difference between arrivals in time interval 0 s plus t and time interval 0 s. That is like number of arrivals in time interval 0 t. This is something like that, memoryless, right? So it doesn't matter how many arrived in this time interval. If you just add the t to this time interval, it's like you have started from scratch. It's like it doesn't matter where it started. Just if it all depends on the length of this interval. Okay, it's that time interval, not the interval itself, the length of the interval. Okay, so example. I have a nice example here. I found solved it and found numbers for you, so it's a good example of this thing. Example. So let's say 6 people on average. So, now these are the questions. In 1 hour. In 1 hour. So, A. Find P of no one arriving in 1 hour. B. Find P of more than, no, 2 arriving in 15 minutes. Right? And C, P, find P of more than 2. Arriving between 10 and 10:45 a.m. Okay, so this is like a typical problem in Poisson process. So we are given lambda, but that is per hour. So it might say 3 people per half an hour. Which is the same as 6, in fact, that we have here, 6 per hour. So it's better to change it into per hour, so you don't have to be careful here. So that is like 6 per hour. Since these are given per hour, you can always change that into per hour. Otherwise, you have to change that into half an hour periods. So. Well, let's find the first one, then I have to erase. So number A, solution. So solution is so we have lambda is 6 arrivals per hour. Okay. So the first one is in 1 hour, so that is N1, which is Poisson of lambda. And we want to find P of N1 is 0, so it is e to power minus lambda times lambda to power 0, 0 factorial, and that is e to power minus 6, which is approximately 0.002479. So with that average of 6 people per hour, there's a small chance that nobody comes in any 1 hour period. So that is the first part A. Let me erase this and do B. Well, let's say this is n of 15 minutes. 15 minutes, 15 divided by 60 is 1 over 4, right? Is it? Yeah. So that's in fact n of 1 over 4. So that's Poisson of 6 over 4. 6 times 1 over 4. Remember, that's lambda t. So that is Poisson of 6 over 4 is, what's that? 1.5, is it? That's 3 over 2, that's 1.5. Okay, so 2 arriving in 15 minutes, so that is P of n 1/4 is 2. And that is e to power minus 1.5 times 1.5 squared over 2 factorial, which is, I calculated this, 0.2510. So in 15 minutes, there is about 25% chance that 2 people arrive. Okay, so this should give you some idea how to solve Poisson, Poisson distribution problems. You have to come up with this number here. It tells you in this period. So if you are given lambda, the average, then turn that into something like this. So find that t. And part C, C is P of more than 2 arrive 10, and 10 45, that's 45. So 45 over 60, that is 3/4. So we are dealing with n of 3/4, and that is Poisson of 6 times 3/4. That's lambda t again. So which is Poisson. How much is that? That is okay. That's to 4.5, right? That's 18/4. Yeah, 4.5. So that's Poisson 4.5. So we need P of n of 3/4 more than 2. So that's 1 minus P of n of 3/4 less than equal to 2. You see, this is more than, so that's less than equal. So that's 1 minus. I just write the e to power minus 4.5. Let's write it at the beginning. Then, so it's like this. So e to power minus 4.5. Then this is 0, 1, 2. 0 will be 4.5 to power 0, 0 factorial. 4.5 to power 1, 1 factorial. 4.5 to power 2, 2 factorial. Okay? So this is, and I found this in English. Did I calculate that? No. Well, anyway, so you can calculate that yourself. I don't know the number here, but it should be, I guess it should be more, because in 15 minutes we had like 0.25, so that should be a large enough number. So anyway, so that is the solution to these three problems. Now let's continue and see what else is related to the Poisson process and why am I doing it here. That's in fact the main part, main reason. Otherwise I discussed Poisson process before and Poisson distribution before. Now, the relation with exponential distribution. So, if I let what is inter-arrival time? That's the time between two arrivals. So I'm sitting here at the door and one person arrives, okay? And I just wait, boom, another person arrives. Wait. Now this time that I spend looking for another one coming in, that's the inter-arrival time. And you have a feeling that this should be random, right? People are not always just getting into a bank just by in any order, right? So the inter-arrival time is the time between the two arrivals, and that is in fact a random variable. Now let T1, T2, Tn. Let me go n plus 1 because I'm finding n plus 1 b inter-arrival times inter-arrival times. We should put them together. Anyway, inter-arrival times. So IE for let's say Tn, no arrival happens in the time interval Tn minus 1, comma Tn, for example. Okay? So nothing happens, no arrival happens between any two of these. And also, each Tn is a random variable taking values in 0, positive, infinity. You see? And it can be any number between these two, any number, right? Any number. So which means what? Which means that Tn is a continuous random variable. So Tn is a continuous random variable. Tn is a continuous random variable, right? So let's find its PDF, or if you find its PDF or CDF or something, then by looking at that we can tell what kind of random variable it is. So let's try to find this thing. And I have a reason that I wrote Tn plus 1. So let's find for Tn plus 1. So let's see what distribution it has. This thing is getting so early, I need to wash it anyway. So we find the CDF. So we need P of T n plus 1 is bigger than T. Okay? If we find this, then we can find the other one, which is the CDF. So we find CDF, in fact, and find its derivative, and that is our solution, right? That's the PDF. So let's see. So what does this mean? P of Tn plus 1 bigger than T means no arrivals in, that's in fact P of no arrivals in, say, n comma n plus T. N plus 1, sorry. Sorry, what am I saying? That is in fact, yeah. N plus T. 1T1 corresponds to 0 and 0T, right? So it's not 0T. Yeah, that's correct. So there is no arrivals in the time interval T that starts at n, in fact. Okay, so that is P of n plus T minus n of small n. Remember, this was what? This was equal 0. But this was what? Remember, I calculated this was in fact equal to nt. So that's like saying that P of nt equal to 0. But remember, that was minus lambda t. Times what? Times lambda t to power 0 over 0 factorial. So this equals in fact e to power minus lambda t. So what is P of t n plus 1 less than equal to t? That is 1 minus P of this thing, t of n plus 1 bigger than t, which is 1 minus e to power minus lambda t. Okay, so what is it? This is CDF of what? Exponential lambda t. Exponential lambda t. Right? So that is in fact an exponential distribution. So each ti is an exponential distribution. And this tells me that if you look at the PDF of well, this is I can say, okay, I know this is in fact f of t. The CDF is 1 minus e to the power minus lambda t, and we have continuous distribution. F of t is derivative of this df dt, and that is lambda e to the power minus lambda t. So this tells me that t n plus 1 is in fact exponential lambda. And since n plus 1 was just a generic point, it means that all ti's are exponential lambda. Okay? So let me draw a picture for you. In fact, that picture makes makes things more clear for you. So it's like this. So if lambda is per hour, for example, and I have 1 hour, say, then this is from 0. So from 0, you wait. Someone arrives. Then you again wait. Someone arrives. 2. Then you wait. Someone arrives. Then you wait. Someone arrives. Then you go over there and wait. Someone arrives, and so on. So between 0 and 1, that someone arrives, that's the waiting time. That's the distribution of waiting time. And all of them are the same. All of them are the same. They have the same distribution. All of them have the same distribution. So that is in fact an amazing way of looking at this thing. At least to me, it gives me a lot of sense what's happening. So at time 0 I'm waiting. And wait, it means that the probability that somebody coming at a certain time obeys this. So if like 2 minutes has passed, I can ask this question: what's the probability that one person arrives after 2 minutes, right? And I know that the distribution of that is exponential something. If 5 people arrive, I can ask that, and that is exponential 5, exp 5. So then I can find the probability that somebody arrives after 2 minutes. So it's like this. So I am sitting here on a chair, say, how can I draw? So I'm on chair, and one person arrives. And I know that Ti satisfies, say, exp 5, that is 5 people per hour. Now I can ask this question: what is the probability that this T of whatever that is bigger than 2 minutes? Okay? So that is in fact integral from 2 to infinity. Lambda is in fact this, 5 e to the power minus 5t dt. But remember that was 1 minus e to the power minus 5 times 2. 1 minus e to the power minus 10. And that's a very small number, so that's almost 1. It's 5.9999 something. If 5 people arrive per hour, then, oh gee, that's 2 minutes, that 2 minutes is wrong. That's 2 hours, sorry. So, gee, that's per hour. My bad. You see, the mistake is that this should go divided by 60, right? So this is 2 divided by 60, not just 2. So that will be, yeah, that's not that small. So it will be 10 divided by 60 minus 1 over 6. Yeah, that's something. So it's not, I don't know what that is, but you can calculate, and that is a probability that one person arrives after 2 minutes has passed. So one person arrives, and then you ask yourself, what's the probability that another person arrives in more than 2 minutes? So after 2 minutes, what's the probability that someone arrives? So that is the probability, okay? So, another thing is, which is also related to this is, that's also very interesting. So let's ask this question. So the relation uniform so this one is uniform distribution and the Poisson process. So let me give you the way that this is. So suppose one person arrived in the interval 0 t0, say, okay? If U denotes the arrival time, then U takes any value in 0 t0, right? This makes U a continuous random variable. Okay, so let's find P of U being less than equal to T, and let T be less than equal to T0 and bigger than equal to 0. Okay, so T is in this interval. So this is P of 1 arrival in 0t, given that there is 1 arrival in 0t0. And we mean just 1 arrival, not more than 1. Right? So this is one event. This is another event, remember? So we are trying to find P of E given F. Remember that formula, P of E and F divided by P of F. So that is P of 1, exactly 1 arrival in 0t, and 1 arrival in 0t0 divided by P of this thing. 1 arrival in 0t0. Okay, So that is, remember that was the formula for P of E given F. And let's erase this and continue here. So what is this thing? This is in fact because there is just one arrival, this is equivalent to saying that P of one arrival in 0t and no arrivals in t comma t0 over P of, what is this? P of one arrival in 0 t0, that is e to power minus lambda 0, no, sorry, that's lambda t0 times lambda t0, right? Over 1 factorial. So I didn't write 1 factorial. So this one and this one are independent. Remember, anything happens in two disjoint interval. This interval and this interval are disjoint. So anything happens in these two are independent. So these two events are independent. So we have P of one arrival in 0t times P of no arrival in t comma t0, right? Well, what is this? This is no arrival. I can say 0 and t0 minus t, right? Remember? That's the same thing. It all depends on the length of that interval. So divided by e to power lambda t0 minus times lambda t0. So one arrival in this time interval, e minus lambda t times lambda t. The other one is no arrival, is simply e to power minus lambda times t0 minus t. Denominator e to power minus lambda t0, which is what? Okay, this is minus lambda t plus lambda t. This goes away. So on top I have e to power minus lambda 0t, lambda t, denominator minus lambda, what am I saying? This is t0. Did I write that anywhere? And denominator will be times lambda t0. So that's t over t0. That's t over t0. So that's t over t0. And what was that? Well, so I found that this thing here, I found that p of this u less than equal to t is t over t0. That's the CDF, right? That's the CDF of some. So what is f of t of that? F of t is df dt, which is 1 over t0. And this is on interval 0 t0. That's on interval 0 t0. So we have in fact proved that this u is uniform time of arrival t0. Okay, so we have found that the time of arrival is in fact has uniform distribution, and that makes sense. So the process was like this. So I start here, and inter-arrival time, and somebody arrives. Then I start again, somebody arrives. Then I start again, somebody arrives, and so on. Somebody arrives, and so on. But in each of these intervals, so this is like t0, when do this person arrive? So, well, this is not t0 in fact, the t0 can be anywhere. So you just, if you take any 0 t0 here, so t0 can be here, so okay. When does this person arrive? if there's just one arrival, so that can't be here. So because I'm assuming that there's just one arrival, so T0 can be somewhere here, right? T0 can be somewhere here, and in this interval, this guy arrives at certain time, right? At certain time. And that time, which is this, has a uniform distribution. In a sense, it's saying that he can arrive at any moment in this interval, right? Remember, uniform was like choosing a point in this interval. So it is saying that this guy can arrive any moment between 0 and T0, if we know that there's just one person arriving. That makes sense. You cannot say, okay, he will arrive this time. No, just any time. So remember, uniform distribution was in fact that. So we have related so many things to this Poisson process. The Poisson distribution itself, the exponential distribution as inter-arrival time, modeling the inter-arrival time, and uniform distribution modeling the time of arrival. So you can see that how all these things are related to each other, and this whole thing in well, I'm not saying the whole thing, but anyway, it's like some Poisson, say, stream, some people call it something. And well, so that was the lecture on Poisson process, and you saw how they are how it is related to these three random variables. Okay, so see you next time.